All right, here are a couple of examples of doing derivatives with natural logarithms. The two specific examples are shown, 3 natural log of 5 over x, and then y equals something pretty complicated with x to the fourth and natural logarithm involved. What I'd like to do first is remind you that you often have two ways to do natural logs because you can transform the way a natural log is expressed by applying the rules of natural logs. I have a little trick. I say the log rolls down the ladder of math. It sounds a little bit esoteric, but if you remember that multiplication is repeated addition, right? It got built up from addition. Downward would be logarithm. So when I see ln of 5 over x, which I've circled, I allow myself to go, I could write that as ln of 5 minus ln of x, right? Logarithm of a division becomes a subtraction when I apply the log. Log rolls down the ladder. I think I'll show it to you both ways. So let's put that in parentheses and put a y equals 3 times in front. Oops, sorry, my parentheses are wrong. A y equals 3 times in front. All right, and we'll work it that way. And I'll also work it the original way. Just y equals 3. Y equals 3 ln 5 over x. I'm going to start with the transform version, the other version, because it looks a lot easier to me. Right? Wouldn't you agree, right? The 3 is just a scalar in front, so it's not going to change. So really, we just take the, right, y prime equals, and then it's 3 in parentheses, logarithm of the first term, which is log of a number is a number, that's 0. And then the natural log of x, we've memorized that derivative is 1 over x. So it seems like this just very quickly simplifies, I was about to say sympathize, simplifies to 3 over x. And that's it. So, right, applying the logarithm first got you something here, got you an easy derivative of two terms, one of which disappeared. Now let's see what happens if we don't simplify the logarithm. It's not mandatory, it just sometimes is easier. So let's go back to the original and do the derivative following the rules of natural logarithm derivatives. Well, it's the same rule, right? When you take the derivative of natural log, you get 1 over whatever was in the parentheses, 5 over x, close parentheses, times, don't forget, there's a chain term, right? The derivative of log of x is 1 over x, but the derivative of log of something complicated involves the chain rule. So the answer is 1 over the complicated thing times the chain term, right? The chain term is the correction factor. I'll break it up into 2 steps so it's a little more obvious. 5 over x is what has to be taken the derivative of, right? The chain term is the derivative of the inside term. So I hope showing that reminds you of how the chain term is working, right? 3, if you don't mind, I'll simplify the first term into 3. 1 over 5 over x looks like 3x over 5. And then what's the derivative of 5 over x? Well, right, I'll just tag this on, right? 5 over x equals 5x to the power -1. And now we can apply the power rule very simply. you can already see this is a much more challenging problem. So what's the derivative of 5x to the negative 1, right? The derivative of 5 over x. Okay, we have to apply the power rule. So we bring down the power, and the 5 stays with us, and x is now to the power 1 lower, right? We always subtract 1 from the power. Oh my goodness, right? This is starting to get kind of crazy. So let's simplify it. Let's see. Let's not lose track of things. All right, so we have a 3x and a 5 on top. I'm going to remind, to help things out here, I'm going to remind you that x to the power negative 2 equals 1 over x to the power 2, right? I flip things around, and that's important because I'm going to have, I'll bring my constants to the front. I've got a negative 1, I've got a 5, then I've got my 3x over 5, and after that, I've got my just over x squared. A lot of crazy stuff going on here. I think I'm going to go to freehand mode here for a moment because it looks like it might be a little easier. You see how we have an x squared on the bottom of the fraction and an x on the top? So negative 1. So that means that the x gets canceled and the x and the squared gets canceled. So I just have over x. And then what's left on the top? Oh, I have a 5 on the bottom of the fraction. Yes, I have a 5 on the bottom of the fraction. And I also have a 5 on the top of the fraction, right? I have this division by 5 and that multiplication by 5. So they cancel. The 5s are gone. And so all that's left is a negative sign and my 3. So it should be negative 3. Whew, that was strenuous. Might have been easier if I'd written in freehand instead of linear text all the way through. Either way you do it, it's quite strenuous and it gets the right answer. Oh, you're saying they don't match over here? Yeah, they do. I just forgot to copy the minus sign there. Let's just consider that. Let's pretend I did that on purpose to remind you that it's really important to keep track of your pluses and minuses when you do calculus. There we go. Same answer, 2 methods. In this case, and I want to emphasize this case, it was more clever to separate the logarithm. The reason I knew that in advance was my experience doing the chain rule. 5 over x is going to be the ln of something complicated. So I'm going to need a chain term if I leave it alone. And I know the derivative of 5 over x is complex, right? It's got a negative exponent, so it's going to get pretty messy. So I automatically, my response would be, let's clear out that fraction and make it a nice, simple difference. And that'll have a nice, much nicer derivative. It's possible just to leave it alone and it's okay, but that would be considering the grind method, not the clever method. And you need a balance of both abilities to do very well on the exam and of course later on in the praxis. All right, let me clear those out of the, let me clear those 2 out and I will go do the other one. There are 2 ways to do this one also, but I think the second way would be what I'd call optional. You don't have to do it that way. This one is very clear as it is. You've got one term that involves a product, right? That's going to invoke the product rule, and another term that's clear polynomial. So, polynomial derivatives are quite easy, so there's no need to mess with things, right? So let's just write it out without doing any computations, right? The product rule, uh, I think that's on your formula sheet. So let's just, let's pretend we're not going to do anything. X to the fourth over 8, take its derivative, times ln of x, and then plus, this time we're not going to touch the x to the fourth over 8, but we're going to take the derivative of ln of x. So we'll put that prime symbol outside it. Oh, sorry about that, messy there. And of course, we're not done there. We have a subtraction term, right? So we're going to subtract, and that's just a simple polynomial. So it's just going to be x to the power 4 over 32, and then derivative, right? I applied the derivative to both terms above. Since the first term is a product, I have to apply the product rule. It's a very simple way to do a derivative carefully and cleanly, without having to carry too much in your head. I would recommend that, even though it's a bit slower, but sometimes you got to go slow to be fast. In other words, if you're slow and deliberate, you'll get it right and you'll get the credit. If you're not slow and deliberate, you might do like what I did before, drop a minus sign, and then you're done for. So y prime, now let's actually do the computations. So here we had the derivative of x to the fourth over 8. So that's 4x cubed. And I'll immediately cancel the 4 with the 8. So I am going to do that invisibly. I'll cancel the 4 with the 8 and give us x to the third over 2. And then I just copy ln x because I have to, because this is a chain product rule. And then for the other one, I leave the first term untouched, x to the fourth over 8. And the derivative of ln x is 1 over x. And then the derivative of x to the fourth over 32, well, again, x to the fourth is 4x cubed, and I'll cancel the 4 with the 32. I don't want to write out every single step, and neither do you, but keep what you don't write to a very minimum. X to the power 3 over 8, because the 4 exponent comes down and cancels 4 out of the 32. And now, as you can see, it's just simplification. The most interesting part of the simplification is in the middle term there, because right, you've got x to the fourth times 1 over x. You're going to cancel one of those x to the fourths. So now you've got a bunch of x cubed terms. So let's go ahead. Let's write it down so we can see it explicitly. And I'm just going to, for my own convenience, I'm just going to copy and paste and then modify the next line. You might want to just copy by hand on a test, on your paper, something like that. 1 over x times x to the fourth, that's just x cubed. And then that means I've taken care of all of this. The rest is just arithmetic. It really is just arithmetic. So I'm not going to spend a whole lot of time on it, but obviously you're going to factor out the x cubed since every term has that in it. And then you'll have a bunch of leftovers. You've got 1/2 ln x. You've got 1/8. Oh, oh, that's cool. I could have just canceled the line before, right? These two terms are the same. Turns out that they're the same when they get reduced. So let me go ahead and highlight that red and go gone. And we just have the x to the cube 1/2 ln x. I still like factoring out the x cubed because this allows me to show an alternative version of the answer. X cubed is still in the front. I'll keep it in parentheses to keep that clear. But it is possible on a multiple choice exam that they might look at the 1/2, and for some reason, they might want this expressed as the logarithm of the square root of X. Not common, but it quote cleans out the fraction. It's sort of a matter, sometimes it's almost a matter of opinion about what's simplifying and what's not. This one is, leaving it untouched like this. It's it's X cubed halves ln of X, right? That's pretty nice. The second version here is X cubed 1/2 ln X. That doesn't look very elegant, and that's why I chose to at least note that you can put it in this way, which is X cubed, right? What would happen if you took, remember, the log rolls down the ladder, so that means an exponent would become a multiple, right? So that means you can take a multiple and make it an exponent. So that's where I got X cubed in the front and ln of X to the power 1/2. And that can be rewritten as X cubed ln square root of X. All right. This is just sort of being playful, which might not actually be playful if the multiple choice doesn't look like it has ln of x's in it. And you go, there's no answer, blah. Wait, just relax, right? You do have a half. If you see square roots, you should think power half. Wait, I have a half in the front. Don't the rules for logs help me do something? So that's the way to calm down if only things like this show up in the answer key and not things like this. So there you go. If it's just ln x, it's pretty simple. Just throw in 1/x. And I believe the major point of the way they set this up with two terms and so on was so these terms would cancel. They just wanted to make sure that you got things right, canceled those out, and just left and just dealt with the remainder. They cooked up the original function so these would cancel. So they're just trying to, make sure you practice it right. And in this one, no special tricks. This one, I believe they cooked it up so that if you apply the chain rule without thinking, then it gets really complex, as we saw. But if you think about, oh, I can use the power of logarithm, just logarithm algebra, not calculus, right? If I just do my logarithm algebra first, then it'll look like something simple for derivatives, a constant, and then just plain old ln x. That's much nicer. No chain term needed on ln x. It's just 1/x. So keep both of those skills in mind. Just doing it when it's ln x and pausing and going, and sometimes using rules of logs backwards if your multiple choice answers look a little weird, or using rules of logs first to make sure when you do the derivative, it feels less complex. The two major things to look out for when you've got natural logarithms in your derivatives.